Hi guys, it's Kate, and this is the first video for week 2 of Math 23B. This week we're going to continue discussing what kind of functions are integrable and exactly how to compute these integrals. For a lot of students who have taken multivariable calculus before, they can tell you that integrating over a region in the plane or a region in space is a little bit more challenging than integrating over an interval as we did in univariate calculus. And so those are the major points that we'll be touching upon in this week's notes. Let's get started. Reviewing what we've already discussed. If we have a bounded function with bounded support, we can say this function is integrable if and only if, for any epsilon greater than 0, we can find a level of dyadic division, usually notated capital N, that does the following. Every single cube at this level of dyadic division is either good or bad. The good cubes are cubes whose oscillation, remember that's the difference between the function's maximum or the supremum of the function's minimum, the infimum of the function values, is less than epsilon. So those are the good cubes. And then there are bad cubes. The bad cubes are the ones whose oscillation is greater than epsilon. And the key here is that at this level of dyadic division, the total volume of the bad cubes is going to be less than epsilon. So we know that a bounded function with bounded support is integrable if and only if, for any epsilon greater than 0, there is a level of dyadic division, n, where the number of bad cubes, the bad cubes themselves, create a set whose total volume is less than epsilon. There are a couple things to point out that sort of follow from this. Note that any uniformly continuous function is integrable since there are no bad cubes. There's not going to be a particular place where the oscillation is wildly different over one dyadic cube than another because this function is uniformly continuous. It's worth reminding ourselves of that definition. Remember, uniform continuity means for all epsilon greater than 0, there exists some delta being the range allowed of the inputs that guarantees that the outputs or the function values will be within epsilon of each other, and that delta interval works across the entire domain that you're talking about. So when you say a function is uniformly continuous along the interval from 0 to 1, that means that for every single epsilon value, there exists a delta, which says if two inputs are within delta of each other, then their function values will be within epsilon of each other. And this delta value works across the entire interval from 0 to 1. You're not going to have a space where that delta range doesn't work. And so you won't have a situation where you have bad cubes. We also walked through a bunch of different examples, and it's notable to remember that even in one dimension, there exist integrable functions that are discontinuous at infinitely many points. Remember, if you don't recall what that looks like, in particular, it was the one where we looked at the function that assigned particular values, ones that very thankfully happen to be decreasing, to the rationals between 0 and 1, and then 0 otherwise. That was at the very tail end of the notes from last week. Make sure to review that if you haven't already. But the principle there was that no matter what epsilon value you selected, there would be a finite number of points where the oscillation was greater than epsilon. And what we ended up doing was we were able to make dyadic division as fine as we could possibly like, so that the total number of bad cubes, in this case bad intervals because we were only dealing in one dimension, would have a total volume less than epsilon. And that goes back to this original statement here. So you can have integrable functions that are discontinuous at infinitely many points. It just depends on the function itself. Another thing to remember is that in 2 or more dimensions, the indicator function for a region like a disk in R2, note that that is the unit circle and the region enclosed by the unit circle, or a ball in R3, that's the unit sphere plus the interior region, must be integrable since it equals the area or volume of the region. Note that it is discontinuous at infinitely many points, the entire boundary of the region. That's where the indicator function goes from 1 to 0 once you land outside of the region. But again, you can capture that entire boundary. You can capture the entire unit circle or the entire unit sphere in a set of dyadic cubes that are of a volume as small as you like. Let's explore that notion a little bit more. This is down here, a useful, sufficient, though not necessary, condition for integrability. A couple vocabulary issues to begin with. We talk about sets of volume 0, which means a set is said to have volume 0 if for any epsilon greater than 0, there's some level of dyadic division where you can capture that entire set with a group of dyadic cubes whose combined volume is less than epsilon. Again, like I said before, that means that a circle in R2 or a sphere in R3 is a set of volume 0. And Paul even sketched this out a bit in lecture, that you can choose a particular level of dyadic division so that all of the dyadic cubes that you need to cover the entire boundary have a total volume less than that epsilon. Note that the rational numbers in the interval 0 to 1 are not a set of volume 0. There's no way to capture all of them in a set of cubes whose volume you can make arbitrarily small. The problem with the rationals is that you can find a rational between any two real numbers. And so what ends up happening is that the entire interval from 0 to 1 has to be covered. It doesn't matter how fine a level of dyadic division or how high your capital N is, that entire interval, every single infinitesimally small dyadic cube will contain a rational in it. And so there's no way to make the total set of dyadic cubes that contain the rationals less than epsilon on the interval from 0 to 1, because there is a rational on every single subinterval, no matter how small it is. So the key for a set of volume 0 is that you're able to capture all of the elements in the set in dyadic cubes that can have a combined volume less than any epsilon. Putting all this together, and note that I edited this a little bit to be more detailed, though your version will have these edits in it, a bounded function f is integrable over a bounded region A if it is continuous, except perhaps on a set of volume 0. So a function can be discontinuous, but those discontinuities have to happen on a set of volume 0. And this right here is going to be your proof 15.1 this week. The proof requires the Bolzano-Weierstrass theorem, and it's actually very similar to the proof that you did last semester, which said that a function that is continuous on a compact set is also uniformly continuous. So a lot of the mechanics behind it are not too different from things you've already seen. As corollaries to this, there are a few other things that we can deduce. One is that if a function f is integrable, and another function g is equal to that function f, except on a set of volume 0, then g is going to be integrable as well, and the two functions will have the same integral. Note that if you modify a function or change it on a set of volume 0, you do not change its integral. Also, if a region A is bounded by a finite union of graphs of continuous functions, and f is continuous over A, then the integral of f over A exists. Note that A is a region in the domain. So if you can take a region in the domain, bound it by a finite union of graphs of continuous functions, say something like the unit disk that's bounded by the following, right? These are the two functions that bound the unit disk. You could also think of the unit ball is bounded by z equals square root of 1 minus x squared minus y squared and negative square root of 1 minus x squared minus y squared. But if you have a region in the domain and it's bounded by a finite union of graphs of continuous functions, and you have a function that is continuous over this region, then the integral of the function over the region exists. And something that's very, very useful, this fact right here, is that any polynomial function is integrable over any set of finite volume. That is a fact that you can certainly take as given and is very, very useful in some of the problem set problems as well as group problems that you'll be working on throughout the course of the semester. So keep that in mind, that polynomials, just as useful as it was to remember that polynomials are known to be continuous functions, polynomial functions are integrable over any set of finite volume.